Copper is a metal that has been essential to human civilization for centuries. It is a versatile material with a wide range of properties that make it useful in many different applications. Copper is essential for modern life because of its excellent electrical conductivity. This property makes it ideal for use in electrical wiring, transformers, and other electrical components. Copper is also a good conductor of heat, making it useful in heatsinks and heat exchangers. The future of copper. Copper is a sustainable material that can be recycled many times. As the world becomes more focused on sustainability, copper is likely to become an even more important material in the future. In addition to its traditional uses, copper is also being explored for use in new technologies, such as solar cells and electric vehicles. As these technologies continue to develop, copper is likely to play an increasingly important role in our lives. Copper processing is a complicated process that begins with mining of ore, less than 1% copper, and ends with sheets of 99.99% pure copper, called cathodes, which will ultimately be made into products for everyday use. The most common types of ore, copper oxide and copper sulfide, undergo two different processes, hydrometallurgy and pyrometallurgy, respectively, due to the different chemistries of the ore. Copper oxides are more abundant near the surface, but are considered low-grade ore, with a lower concentration of copper, although this requires more ore to be extracted and processed. This process is less expensive, so oxides can still be mined at a profit. On the other hand, while copper sulfide ores are less abundant, they contain higher amounts of copper. Although the processing costs are higher, ultimately more copper can be extracted. Since each mine site is unique in its mineral composition, concentration, and quantities, the most economical and profitable processing of ore must be determined by the mine planners. When it is economically feasible, a mine may extract both types of copper minerals. When it is not possible, mines will only process either the copper oxides or the copper sulfides. The first steps of copper processing are the same for both ores: mining and transporting. Copper mining is usually performed using open-pit mining, in which a series of stepped benches are dug deeper and deeper into the earth over time. To remove the ore, boring machinery is used to drill holes into the hard rock, and explosives are inserted into the drill holes to blast and break the rock. The resulting boulders are then ready for hauling. Specialized haul trucks, Conveyors, trains, and shuttle cars can all be used to haul the ore from the blasting site to the processing site. The size of the equipment needed to haul the tons and tons of ore is gigantic. Most ores are then sent through a primary crusher, which is typically located very close to or sometimes in the pit. This primary crusher reduces the size of the ore from boulder to golf ball-sized rocks. Processing of sulfide ore. Sulfide ores are generally processed using pyrometallurgy, the extraction and purification of metals by processes involving the application of heat. This process uses a series of physical steps and high temperatures to extract and purify copper from copper sulfide ores in 4 basic steps: 1. Froth flotation, 2. Thickening, 3. Smelting, and 4. Electrolysis. Following mining, transporting, and crushing to a consistent gravel or golf ball size, the crushed ore is further processed at a mill using secondary crushers and reduced to pebbles and finally to fine sand. After the copper ore is crushed, liquid is added to make it a slurry. The slurry is a mix of valuable copper ore minerals and worthless rock, called gangue, pronounced gan. The slurry is placed in a tank and a process called froth flotation is used to separate the copper minerals from the gangue. Chemical reagents called collectors are added to the slurry and bind to the copper particles, making them hydrophobic or waterproof. Pipes are used to blow air into the bottom of the tank to create bubbles, which rise to the surface, taking the waterproof copper sulfide particles along. The froth of copper-rich bubbles at the top of the tank is then skimmed off for further processing. The gangue sinks to the bottom of the tank to be removed or disposed of as mine tailings. The next stage after froth flotation is the thickening stage. The froth is poured into large tanks called thickeners. The bubbles break and solids from the froth solution settle at the bottom of the tank. The solids are then filtered to remove excess water, which can be reused in processing additional batches of sulfide ore. The final product of the thickening stage is a combination of 30% copper and other metals. This copper concentrate is then sent to the smelter. At the smelter, high temperatures are used to further purify the ore in a series of smelting steps. The copper concentrate is first sent through the smelting furnace to be heated up to 2,300 degrees Fahrenheit and converted into molten liquid. The heated liquid is poured into a slag settling furnace. This step produces a combination of matte, a mixture of copper, sulfur, and iron, and slag, a dense, glassy material made of iron, silica, and other impurities. The copper matte created by the smelting furnace contains 58 to 60% copper. The molten matte is then taken to another furnace called a converter to have the remaining iron and sulfur burned off. The product is referred to as blister copper, which contains 98% copper, and taken to the anode smelter. The blister copper is yellow. When the oxygen in the copper is burned off in the anode smelter, it turns a blue-green color. The resulting product, molten anode copper, is poured into molds called anode casting wheels. The cold anode slabs are 99% pure copper, are now copper-colored, have two handles, molded on top, and are 2 inches thick, 3 feet wide, 3.5 feet high, and weigh 750 pounds. The copper anode slabs are then refined in a final step, called electrolysis. The anode slabs are hung in a large tank full of an electrolyte solution made of copper sulfate and sulfuric acid. Thin sheets of pure copper, which are called cathodes and weigh about 15 pounds each, are hung in between the anodes. An electric current is applied, and positively charged copper ions, called cations, leave the anode, positive electrode, and move in solution through the electrolyte solution to be plated on the cathode, negative electrode. Other metals and impurities also leave the anode to drop to the bottom of the tank or stay in the electrolytic solution. These impurities are collected and may be refined to recover other metals, such as silver and gold. After 14 days of electrolysis, the anodes have gradually disappeared, and the copper cathodes now weigh 375 pounds each and contain 99.99% pure copper. The cathodes are taken out of the tank and rinsed with water to prevent further reaction. The finished copper cathodes can then be made into wires, plates, tubes, and other copper products. Cables are essential components of modern infrastructure. enabling the transmission of electricity and data across vast distances. The production of cables involves a meticulous process that combines advanced technology and skilled craftsmanship. Conductor manufacturing. The cable production process begins with the manufacturing of conductors, which serve as the core for transmitting electrical signals. Conductors are typically made from high-quality metals, such as copper or aluminum. The process starts with the continuous casting of copper or aluminum rods, followed by extrusion or drying to achieve the desired conductor diameter and length. These conductors are carefully inspected for quality and consistency. Stranding. After the conductors are manufactured, they undergo stranding, where multiple conductors are twisted together according to the cable's design requirements. Stranding provides flexibility, durability, and reduces electromagnetic interference. The stranding process can vary depending on the cable type, with different stranding patterns and lay lengths employed to meet specific performance characteristics. Insulation. Once the conductors are stranded, they proceed to the insulation stage. Insulation involves the application of a protective layer over the conductor surface to prevent electrical leakage and external interference. Various insulation materials are used, including polyethylene, PE, polyvinyl chloride, PVC, or cross-linked polyethylene, XLP. The insulation thickness is carefully controlled to meet safety and performance standards. Shielding and armor. Certain cables require shielding or armor layers for additional protection against external factors. Shielding materials, such as aluminum or copper tapes or braids, are applied to mitigate electromagnetic interference. Armor, such as steel wire or aluminum plastic tapes, provides mechanical strength and protects against physical damage. These layers are carefully applied using specialized machinery and techniques. Jacketing. Following insulation and shielding, cables may undergo jacketing, which involves applying an outer protective layer. The jacketing material is selected based on the cable's intended application, considering factors such as UV resistance, flame retardancy, and environmental durability. PVC, PE, or thermoplastic elastomers, TP, are commonly used for jacketing. The outer jacket provides mechanical strength, moisture resistance, and environmental protection.